Hey guys, all right, we're going to do another comparison test. So we're going to do the limit comparison test and the direct comparison test. Okay, so we're going to start off with the direct comparison test. This is going to be DCT. Okay, when we compare two functions, we're trying to find a function that is smaller, that's a little less complicated. Okay. So if I have kind of a complicated function, I want to find one that's smaller than it, that that converges, but I can compare it with. So if a larger series converges, then the smaller series must also converge. Okay. So in this case, we would want the larger one to be the one that we're comparing to the smaller one. Okay, and I'm going to go through some examples of this. The larger one is most likely going to be the less complicated one in this scenario. Okay, so there's two different scenarios. And then if we have a smaller series that diverges, then something that's bigger than it is also going to diverge. Okay, so in this case, the larger one would be less complicated. So this is not, okay? So larger is less complicated if we're doing converging, and larger is less complicated if we're doing smaller. So what we're trying to say is that if I have a function, okay, if I have a function that I know diverges, so I already know that this diverges, okay? Let's say this is a to the n, b to the n, we mix those up, okay? Then I'm going to compare it to something that I know, and I'm going to say, all right, well, this one is even bigger than this one, so it's going to diverge still, but it's going to diverge even a little bit higher, which isn't necessarily true, but it's just a good drawing to show you what that's looking like, is that if this one is smaller and this one is bigger, if the small one diverges, then the big one has to. Okay, in the same sense, if we have a number that's smaller or a bigger number that's converging, and then we have an even smaller number, it's also going to converge. So let's put this into some notation for you, okay? So what we're saying is if b to the n converges, then a to the n also converges. And this is always going to be a to the n is smaller than b to the n. So a to the n is the smaller series, okay? Now, we don't always have to use a to the n and b to the n. Those can get kind of confusing, but you do have to understand that the one that you're comparing it to does have to converge if that's what you're trying to prove, or diverge if that's what you're trying to prove. So sometimes the name of the function gets a little bit confusing, okay? So an is smaller, bn is larger. So that's what we just have to make sure. So if bn that is larger converges, then a smaller one will also converge, okay? So bn's larger, it converges, so a smaller one would also have to converge. Then if an, remember an is smaller, if the smaller one diverges, then I know for sure the bigger one, larger, is also going to diverge, okay? So looking at some examples. So my first example is 1 over 1 plus 2 to the n. And we're trying to see if this converges or diverges, all right? So we're going to use the direct comparison test just because that's what we're learning about, but there might be another test that we can use to do this, okay? So I want to think of something that I can compare this to that's an easier function. So usually we can just look at the power. So we're going to say compare to the sum. So we're also using our sigma notation. n equals 1 to infinity. But this time we're doing 1 over 2 to the n. Okay? So 1 over 2 to the n, I know what this is. This is like 1/2 to the n, right? So this is a geometric series where the r is 1/2, which is smaller than 1. And so this series converges by GST. Okay? So we have to prove what this series does first. If this series converges, now I have to show that this series is bigger or smaller, whichever one we're doing, than the one that we're looking at. So if I've got 1 over 1 plus 2 to the n as one of my functions, and the other one is 1 over 2 to the n, which one's smaller? The bigger denominator is smaller, right? So we have to show this statement right here. This is smaller than this, okay? So we've proved that this one converges. I know that this one converges, okay? So if a bigger function converges, then the smaller one also converges, okay? And remember what we're talking about is that this is an and this is bn. An's always smaller. And you don't have to write this. I just want you to see how those work. So this is an and this is bn. An is smaller than bn. Bn converges. So an also has to converge by dct. So we say n equals 1, 1 over 1 plus 2 to the n. You could also say the series, right? Because that's what we're talking about. The series converges by the direct comparison test. Okay, so we have to state what we're comparing it to. We have to state if that's converging or diverging. We have to state that an is smaller than bn if we're doing converging. And then we have to show that it converges by the dct. So I've already stated that this converges by the GST, but that wasn't our original problem. So we have to go back to our original and always finish up our answer. Okay. All right. So let's look at the next one. So, and then I want you to look at this too. And notice that this is 1 over n minus 2, and n is greater than 3. So this denominator is getting bigger and bigger and bigger, and the limit is going to 0. So I cannot use NTT because the limit is going to 0, right? So that's why we're looking at these other tests. All right, so compare to the sum of 1 over n. Okay, 1 over n doesn't take very much work. It is a p series where p equals 1, and it's a harmonic. Remember, it's our special function that we call harmonic, and the harmonic always diverges. Okay, so you could either write p equals 1 and then go through the PST test, or you could just do harmonic diverges. So we've compared to this. Our less complicated function diverges, and which one out of 1 over n and 1 over n minus 2 is smaller or larger? My denominator is smaller here, a little bit smaller, just by 2, but it's still smaller. And so that means it's a larger overall, right? So 1 over n is less than 1 over n minus 2. And I've shown that this diverges. So if something smaller diverges, if I keep going bigger, it's still going to diverge, right? So the series diverges by dct. Okay, and this one, number 3. We've got 1 over the square root of n plus 1. What should we compare this one to? What would be something that's less complicated than this? What you're thinking of. So right off, you might be thinking 1 over root n. Okay, so if I do 1 over root n, then p equals a half, right? And when we do a half, it's less than 1. And so when it's less than 1 on a PST, then it diverges by PST. Okay. So if it diverges by PST, which one of these is smaller? So the 1 over n plus 1 is smaller than 1 over root n. So I've said that the larger one diverges. And when I do the diverging, it has to go forwards this way, right? So since I'm going backwards, this doesn't work. This is a dead end. Okay, I can't use 1 over root n because 1 over root n is larger. I need something smaller to compare it to. So what's something that would be smaller than 1 over root n plus 1? What about just 1 over n? Is 1 over n smaller than 1 over n root n plus 1? Yes, because this is a square root, so this number is smaller. If the denominator is smaller, the whole overall picture is bigger. Okay. So 1 over n is smaller than 1 over root n plus 1. So now we've got it going the right way, right? Oh, I missed one step. We do want to say that this diverges harmonic, which we already wrote down on the other one. Okay. Diverges harmonic. So if this diverges, then a number bigger than it will also diverge. Diverge by dct. Okay. All right. So you could see how it doesn't always work. You have to be careful about what function you pick, or you'll be doing a little bit of extra work, but it should not be too bad. Okay. And now we've got the limit comparison test, the LCT. So in the LCT, we are going to have 2 conditions. We're going to divide AN over BN, which means, and they both just have to be greater than 0, okay? So AN over BN, positive functions. When I divide them, I have to get a limit. I have to find a number. It doesn't matter what the number is, it just has to be 1 positive and 2 a number, finite. Okay, so these are the conditions of the limit comparison test. So we want to use the limit comparison test when we have a really messy algebraic series and we want to turn that into a p-series to compare it to. Because I know if I do a limit as n goes to infinity and I divide a function by a function, I can use my horizontal asymptote rules, right? So we're going to use our horizontal asymptote rules. To figure out what those limits are. Just a reminder of those rules. If the numerator power is smaller than the denominator power, then the limit is 0. If they're equal, we divide coefficients. And then if n is greater than the denominator, then we don't have an asymptote. It's going to be and behavior asymptote. So it's not going to go to a finite. I should say there's not a finite limit. So the limit is 0 here. The limit is a finite number here. And then this one's probably infinity or something that's not something that you can divide. Okay. So our last one, our goal on this one is we want to be able to compare the two function powers to be equal. Okay. So remember we're dividing two functions. So let me just make sure that I write the an on top. Okay. So an equals 1 over 3n squared minus 4. Okay. So if I divide 1 over 3n squared minus 4, and I divide that by, let's say bn is a less messy algebraic series that has a 2 as the highest power. So we divide that by 3n to the negative 2, right? Or let's just write it as 1 over 3n squared, since we're dividing. So 1 over 3n squared. Okay, so this is our an, and this is our bn. We're dividing these, and we're taking the limit as n approaches infinity, and then I'm finding what that limit is. Okay, so when we do that, when we divide a fraction by a fraction, it turns into multiplication of the reciprocal. And that will be the only time I'm going to write that whole step out. I'm usually going to go right from here to here. Okay, so I'm dividing these two functions together. We're comparing still, so these are comparison tests. So we're going to say we're comparing to this. Okay, so an over bn, and I'm going to get equals 1. Okay, I could have done, instead of comparing to 3n squared, I could have just compared to 1 over n squared, and I still would have had the n squareds are the same, and I would get 1/3. All that matters here is that this limit is finite and positive. It doesn't matter what it is. Okay, so you can't go wrong with what you pick. You want to do an easier one so that, because the whole reason why we're doing this is to say, if this is true, then whatever I compared it to, if this function converges, then this will also converge. Okay? If this function, the one I compare it to, diverges, then my messier one will also diverge. So you want to do one that's an easy to figure out if it diverges or converges. So here, this is p equals 2. 2 is greater than 1. So on the PST, is it converging or diverging if it's greater than 1? Make sure I'm writing all my stuff. Okay, so the one we compared it to converges by PST. And so if this is true, then this function the sum of this function, or this series, also converges. And that was by the limit comparison test. Okay. All right, let's do number 5. An is the square root of n over n plus 7. So I have to think about, I want these powers to be equal. The power on the bottom is a 1, and the power on the top is a half. So what do I want to multiply this half by to get a 1? hopefully you're thinking another half. So I'm going to compare this to 1 over root n. Remember that when we write our limit, let's finish this real quick. So compare to 1 over root n, p equals a half, which is less than 1. If it's less than 1, it diverges. Okay, so I compared it to this function. I said what p is, and that diverges. So now I'm going to do my limit comparison. Okay, and remember I told you I'm not going to do the divide anymore. I'm going to go straight to the flipping it over. So I'm going to do the reciprocal of 1 over root n, and this will be root n over 1. So notice if I multiply root n times root n, I just get n. And then n divided by n plus 7. I'll write it one more time just to make it clear. Equals 1. Okay, that limit is positive and finite. So that means my function that I'm looking for will do whatever this one did that I compared it to. So it will also diverge by LCT. Okay. All right, one more example. Should draw lines like this, show where our steps are. Okay, so I've got n on top and 4n cubed plus n squared plus 5 on the bottom. So how can I get this top to be the same as the bottom? So remember, we're trying to get those powers to be the same. I need to multiply the top by an n squared, right? N squared and another n is n cubed. Okay, so an is the original function. Bn, I'm going to do 1 over n squared. Okay, so we're going to compare to the limit of 1 over n squared. P equals 2, which is greater than 1. When it's greater than 1, it converges. And remember all of these rules. If it's P and it's greater than 1, it converges. All right, so here's our comparison. Here's y, and here's our answer. Okay, so let's do our limit as n approaches infinity of our function. Multiplied by the reciprocal of b. And we're always going to get the same powers because that's how we set it up to work. Okay, so when I take the limit of the n cubed divided by the 4n cubed, we get 1/4. 1/4 is a positive number, and it is a number. So it's positive and finite. So our original function will do whatever our compared function did, so it will converge by LCT. Okay, all right, I know it's a lot of writing, but hopefully you understand the comparison functions, and we will go over them more tomorrow. Have a good night.